Um, so when you look up at the night sky tonight, you aren't actually looking at stars. You're looking at billions of other suns.
Yeah, it is really the ultimate perspective shift. Because, we grow up drawing stars as these little five-pointed geometric shapes on a ceiling.
Right, like decorative stickers.
Exactly, almost like stickers. But the reality up there is, well, it's so much more violent and just it's so much more magnificent.
Welcome to today's deep dive. We are tackling a subject that is going to completely rewire how you, yes, you listening, how you experience the world once the sun goes down.
Because usually when we look at a map, right, like if you pull up navigation on your phone, there's this expectation of a flat, fixed reality.
Yeah, a dot is a city, a blue line is a river.
Right. Everything exists on this comforting, two-dimensional layout that you can just trace with your finger.
And we kind of apply that exact same flat map logic to the sky. I know I do.
We all do. We treat the night sky like a painted dome over our heads. But the moment you strip away that illusion, that 2D concept completely falls apart.
Totally.
You realize you're standing on the edge of this three-dimensional deep space puzzle with absolutely no top and no bottom.
Which is wild. So our mission today is to give you a completely new map. We're going to tailor this celestial navigation specifically for an observer standing outside in India.
Which is a fantastic vantage point, by the way.
It really is. We want to take those random, chaotic pinpricks of light and turn them into a neighborhood you can actually understand and navigate.
But before we can draw the map, we really need to understand what it is we're actually mapping.
Right, okay. So you mentioned earlier that almost every single dot of light up there is a sun. How literal are we being here?
Oh, I mean, completely literal. The vast majority of the stars you can see with your naked eye are massive nuclear engines.
Oh.
Yeah, they're powered by the exact same mechanism as our own sun, which is nuclear fusion.
Okay, let's break that down for a second, because nuclear fusion is one of those terms we hear a lot, but, we rarely stop to actually define it. What is physically happening up there to create that light?
So imagine gravity so unimaginably strong that it takes hydrogen atoms and just crushes them together.
Literally forcing them to fuse.
Exactly. They physically fuse into helium. And that collision, that merging process, releases a colossal amount of energy.
Right.
That violent explosion is what a star is. It's an ongoing, controlled nuclear detonation in the middle of space.
That is terrifying and amazing.
And what's truly humbling is that many of the stars you see when you step outside, they actually make our sun look incredibly average.
Okay, give me an example. Let's say I'm looking up at Sirius, which always catches my eye because it's just so incredibly bright.
Sirius is a perfect example. It's roughly twice as massive as our sun, but it burns significantly hotter.
Twice as massive.
Yeah, and because it's so hot, it pumps out about 25 times more light than our sun does.
25 times.
So you aren't just looking at a pretty twinkling diamond, right? You're looking at a raging, oversized furnace.
That immediately makes the sky feel so heavy. And here's where it gets even wilder. We aren't just talking about lonely suns burning in the dark either.
No, not at all. Modern astronomy has essentially proven that planet formation isn't some rare, miraculous anomaly.
It's actually super common.
It is a completely standard byproduct of a star forming. The data we've gathered in recent years, heavily driven by tools like the Kepler Space Telescope, it completely revolutionized our understanding of this.
Because Kepler essentially just stared at a patch of sky for years, right?
Yep. Just staring, waiting for these tiny, almost imperceptible dips in the light coming from those stars.
Like a shadow passing in front of a street lamp.
A very, very tiny shadow, yeah. When a planet orbits its star and passes between that star and our telescope, it blocks a fraction of the light.
Right, it dims it just a little bit.
Exactly. And by measuring those shadows, astronomers realize that almost every star out there likely has at least one planet, and many have entire systems.
Exoplanets. Planets orbiting other suns. Which basically means our solar system isn't unique at all.
Not even a little bit. It's just one house on a very, very long street.
A street that contains what, like somewhere between 100 to 400 billion houses?
Yeah, that's the rough estimate of how many stars are just in our local galaxy, the Milky Way.
That's insane. So when you do the math, we're talking about hundreds of billions, potentially trillions of planets just in our own galactic neighborhood.
Trillions. Yes.
Think of the Milky Way as our home city. Every distinct light you see with your naked eye when you look up is like a street lamp or a house light in our own city.
That is a crucial distinction. The boundary of human vision basically stops at the edge of our galaxy when it comes to seeing individual stars.
Wait, really? We can't see individual stars in other galaxies at all. What about Andromeda? I hear about Andromeda all the time.
Andromeda is roughly 2.5 million light years away.
Oh, wow. Okay.
So to continue your city analogy, Andromeda is like a completely different metropolitan area that's so far away on the horizon you just can't see its individual street lamps anymore.
Just blends together.
Right, you just see a faint collective smudge of light. On a perfectly clear dark night, you might spot Andromeda as a tiny fuzzy patch.
But no distinct stars.
You will never resolve a single star within it using just your eyes. Every sharp point of light you see is local.
Okay, so once we realize we're looking at our local cosmic city, the very first question that pops into my head is, who is our immediate next door neighbor?
Naturally.
Right, like if I walk out onto my balcony in India tonight, can I see the closest star to our solar system?
So this is where the physics of the space plays a really brilliant trick on us. If we're asking strictly about physical distance, the absolute closest star to us is Proxima Centauri.
Okay.
It's roughly 4.24 light years away.
Which, just to throw this in, is fascinating because astronomers have actually found a planet orbiting it, right? Proxima Centauri b.
Yes, they have, and it sits right in the habitable zone.
Meaning it orbits at just the right distance from its star, where it's not too hot for water to boil off and not too cold for water to freeze.
Exactly. It's in that Goldilocks region where liquid water could theoretically exist on the surface.
Incredible. Okay, so 4.24 light years away. Can I walk outside and see it tonight?
Not a chance.
Wait, why not?
You absolutely need a telescope. Proxima Centauri is what we call a red dwarf star. Red dwarfs are much smaller than our sun, much cooler, and they burn their fuel very, very slowly.
So they aren't pumping out that massive amount of light.
Right. Because of that, they emit very little visible light. It is incredibly dim.
So you're telling me the absolute closest star to Earth is completely invisible to the human eye?
It is completely invisible.
That is wild.
So, astronomers look for the closest star you can actually see, and that would be the Alpha Centauri system.
Okay, and how far is that one?
About 4.37 light years away. It's actually a three-star system, and it contains a sun-like star that pumps out enough light for us to see.
And there's a massive catch here for our listener.
There is.
If you are standing outside in India or, really anywhere in the Northern Hemisphere, you cannot see Alpha Centauri either.
Nope. The Earth itself is literally in the way.
Right.
Because of India's latitude on the globe, Alpha Centauri is permanently hidden below the southern horizon.
So I'd have to travel south to see it.
You would have to travel down to the southern hemisphere, yes.
Okay, let me get this straight. We can't see the closest star because it's too dim.
Correct.
And we can't see the second closest because the literal planet we are standing on is blocking our view.
Also correct.
So who is the closest visible neighbor for someone looking up from India?
That brings us right back to Sirius.
Wow, okay.
And Sirius is 8.6 light years away.
Wait a minute. So the closest star I can actually walk outside and see tonight is literally twice as far away as the stars that are physically closest to us.
Yep. If we connect this to the bigger picture, it beautifully illustrates the core illusion of the night sky. Well, when you look up, you instinctively assume the brightest stars are the closest ones.
Right. Yeah, that makes sense.
But brightness completely trumps mere proximity. Sirius dominates the sky, not because it's close, but because of what we discussed earlier.
It's a massive raging furnace.
Exactly. It outshines closer, quieter stars.
Okay. To really wrap our heads around this distance, let's use an analogy, because 8.6 light years is hard to picture.
It is very hard.
Imagine our sun, this massive blinding sphere of plasma that could fit like 1 million Earths inside it. Imagine it shrunk down to the size of a beach ball, just 1 meter wide.
Okay, that's a useful visual.
Right. So if our sun was a 1 meter ball sitting in the middle of a room, Proxima Centauri, our absolute closest neighbor, wouldn't be in the same room.
No, it wouldn't.
It wouldn't even be in the same building.
Yeah.
In that scale, the closest star would be roughly 300 kilometers away.
Let that sink in. You have a 1-meter object, and you have to drive for hours at highway speeds to reach the very next 1-meter object.
That is just wow.
That is the density of our universe. The sheer amount of empty, freezing void between these massive fusion engines is, well, it's almost incomprehensible.
Makes me feel incredibly small. But also, desperate to make sense of it all.
Sure.
So knowing that Sirius is our brightest local neighbor, and that the sky is this vast, impossibly spaced out 3D ocean,
Hmm.
How do we actually go out into the Indian night and find anything?
You need an anchor.
Right, because if the brightest thing isn't the closest thing, we can't just trust our eyes to map it out.
Exactly. You cannot just wander visually. For an observer in India, your ultimate starting point is a constellation called the Saptarishi.
Which is known in Western astronomy as Ursa Major, right? Or the Big Dipper.
Yes, it's that grouping of 7 very bright stars that look exactly like a large spoon or a ladle in the sky.
Right. Finding that spoon is step one.
And the reason Saptarishi is so critical for observers in India is because it is largely a circumpolar constellation from that latitude.
Okay, let's translate circumpolar for everyone. What does that actually look like to the person standing outside?
So, because of where India sits on the Earth's surface, those stars don't rise in the east and set in the west like the sun does.
Oh, they don't.
No. Instead, they essentially spin around the North Pole, kind of like a record on a turntable.
Oh, I see.
They stay visible high in the sky, turning in a circle, rarely dipping below the horizon.
So it's basically a permanent fixture.
A permanent fixture that acts as a pointer. If you take the 2 stars that make up the front bowl of that spoon shape and you draw an imaginary line through them,
Right.
they point straight to Polaris.
The North Star.
And Polaris is the true anchor.
Why is that one the true anchor?
Because the Earth's axis of rotation points almost directly at it.
Huh.
As the Earth spins through the night, all the other stars appear to arc and move across the sky. But Polaris, it stays almost perfectly dead center, fixed in place.
Okay, here's where it gets really interesting for me. Finding the North Star isn't just a neat party trick, it is literally locking in your cosmic compass. Once you have north locked in, you just turn around to face south. You let the seasonal highways guide your eyes to the rest of the neighborhood.
I love that phrase. Seasonal highways is highly accurate. Because while Polaris is always parked in the north, the rest of your view changes completely depending on the time of year.
Because we're orbiting the sun.
Right. As the Earth orbits the sun, our night side faces outward into totally different sectors of the Milky Way galaxy.
So what we see depends entirely on where we are in our orbit. And for observers in India, the absolute best, most rich time for stargazing is the winter.
Winter offers 2 distinct advantages in India. First, the atmosphere is generally crisper, there's less humidity, less distortion.
Makes sense.
Second, the winter sky actually faces one of the most dynamic, star-rich spiral arms of our galaxy.
Okay, so it's a winter night. You found Polaris in the north. You turn around and face south. What is the first highway marker you're looking for?
You look for Orion the Hunter. Yes, it is arguably the most recognizable shape after the Saptarishi. You're looking for 3 distinct, incredibly bright stars, perfectly spaced in a tight, short line. That is Orion's belt.
And it's framed by 2 fascinating stars, right? In the upper corner, you have Betelgeuse,
Yes.
which, if you look closely, glows with this really distinct reddish tint. And then in the opposite lower corner, you have Rigel, which blazes in this brilliant blue-white.
And those colors aren't an optical illusion, by the way. They actually tell you about the star's temperature.
Really?
Yeah, blue stars like Rigel are insanely hot, while red stars like Betelgeuse are cooler. I mean, still unimaginably hot by human standards, but comparatively cooler.
Got it.
But once you find Orion's belt, you basically have the master key to the winter sky.
Because it points right to our neighbor. If you take the line of Orion's belt and follow it downwards, just tracing it across the sky, it points like an arrow straight to the brightest star you will ever see in the night sky.
Serious. The raging furnace, 8.6 light years away. You have now navigated from the North Pole directly to your closest visible neighbor.
And Orion guides you to other neighborhoods too, doesn't it?
It does. If you follow the belt in the opposite direction, so upwards instead of downwards, you run right into Taurus, the bull.
Okay.
You'll see Aldebaran, which is a bright orange star, and just past it, the Pleiades.
The Pleiades is amazing. It looked like a tiny, blurry, miniature replica of the Little Dipper. But it's actually a cluster of young, hot stars born from the same cloud of gas.
It is a phenomenal sight. And you also have the constellation Gemini nearby, marked by the 2 bright twin stars, Castor and Pollux. The winter sky is just incredibly dense with landmarks.
It really is a map. You find the spoon, you lock in north, you turn south, you find the belt.
Yeah.
You follow the belt down to the brightest star, you follow it up to the cluster. It's literal step-by-step navigation.
Exactly.
But then the Earth keeps moving, summer arrives, and we completely lose Orion.
We do. Orion slips into the daytime sky where the sun washes it out. But the summer night sky from India brings its own massive feature. You want to look directly overhead for the summer triangle.
Which is a shape so huge it actually borrows stars from 3 entirely different constellations.
Right. You have Vega, an intensely bright blue star in the constellation Lyra. You have Deneb, which forms the tail of Cygnus, a constellation that looks like a giant cross or a swan flying down the Milky Way.
And the third one.
Altair in the constellation Aquila. Those 3 stars create this unmissable, massive triangle high in the summer sky.
So practically speaking, for the person listening to this who wants to walk onto their roof tonight, how do they set themselves up for success?
Time and tech. Aim for the hours between 8 p.m. and 11 p.m., basically before the night dew or fog settles in too heavily.
All right.
And you must try to escape the direct glare of city lights. Light pollution will wash out all the faint guide stars, leaving only the brightest anchors visible.
Which makes it really hard to trace the constellations.
Exactly. And take advantage of modern tools. Download a stargazing app like Stellarium to your phone.
Oh, I love those apps. You literally just point your phone at the sky, and using your GPS and gyroscope, it overlays the entire map onto your screen in real time.
It takes the guesswork out of finding Orion's belt or Saptarishi.
Yes.
It is the ultimate training wheel for cosmic navigation.
It really is. But there's a twist to this map. We've established the fixed landmarks, the Saptarishi, Polaris, Orion, the Summer Triangle, but not everything up there follows the rules. There are objects moving through this map actively rebelling against the fixed grid.
You're talking about the planets, and this is a massive point of confusion for beginners.
Oh, totally.
Planets are not stars, and they're not fixed within the constellations. The word planet literally comes from a Greek term meaning wanderer.
Why do they wander while the stars stay still?
Because of scale.
Wow.
The stars are so unfathomably far away that their physical motion through space just isn't noticeable over a human lifetime.
They appear totally static.
Right. But the planets are right here in our backyard. They're orbiting the sun along with us. Because they're so close, as they move through their orbits, we can physically see them change position night after night against that distant, static background of the stars.
And so who are the wanderers we can actually spot from India?
Venus is definitely the most dramatic. It is the brightest object in the sky after the moon. But because it orbits closer to the sun than we do, you only ever see it near sunrise or sunset.
The morning or evening star.
Exactly. Jupiter is also incredibly bright and stays visible for months at a time, moving very slowly. Mars gives off a very distinct, rusty red glow. And Saturn is visible too, though dimmer and more yellowish.
Okay, so behind all of this, behind the wandering planets racing around our sun, behind Sirius, our close neighbor, behind the giant stars of Orion, there is the ultimate backdrop.
Yes.
If you manage to get out of the city in India, like far away from the streetlights, to a truly dark sky, you might look up and see a faint glowing white band stretching across the dark.
It looks almost like a thin wisp of high-altitude cloud that just refuses to blow away.
But it isn't a cloud.
No, that is the Milky Way.
Our entire galaxy.
To really understand why it looks like a band, you have to picture the shape of our galaxy. The Milky Way is a flat, spinning disk of stars, kind of like a massive cosmic pancake.
Okay, a pancake.
Our solar system is embedded inside that disk, about halfway out from the center. When you look up and out of the flat part of the disk, you see a scattering of individual stars.
Right.
But when you look along the plane of the disk, looking edge-on through the thickest part of the pancake.
You're looking through tens of thousands of light years of dense space.
Exactly. There are so many billions of stars packed into that line of sight that your eyes just can't separate them. Their light blurs together into a continuous milky river of light.
Wow.
You are physically seeing the architecture of the galaxy you live inside.
This raises such an important point. This is exactly what I mean when I say you have to dismantle the idea of the sky as a flat ceiling. Think about the layers of depth we are talking about here.
It's staggering.
When you look at Jupiter, you are looking at light that is just minutes away. When you find Sirius, your closest visible neighbor, you're looking 8.6 light years away.
Right.
When you trace Orion, you're looking hundreds of light years deep. And when you see that glowing band of the Milky Way, your eyes are absorbing light from tens of thousands of light years away.
And all of those varying depths, all of those radically different distances, they exist in the exact same field of view.
It's a 3D ocean.
You are looking through a 3D ocean of space, past the close neighbors, through the mid-distance landmarks, all the way to the dense edge of the galactic city limits.
It is an incredible amount of information hitting your retinas all at once.
Yeah.
I feel like our mission today was to take the Indian night sky and turn it from a chaotic scattering of dots into an organized map.
And hopefully we have. You now know that almost every point of light is a raging nuclear sun, likely hosting its own system of planets.
Yep.
The brightest stars aren't necessarily the closest, as Sirius brilliantly proves.
You know the Saptarishi is your permanent compass, pointing to the unmoving North Star. You know to look for Orion in the winter to guide you to Sirius, and the massive summer triangle when the weather turns hot.
You know how to spot the wandering planets against the static background, too? And you know that faint glowing cloud is the edge of our galactic home?
You have the map. But before we go, there is one final reality about this map that takes everything we've discussed and twists it just one step further.
Oh, yeah.
It has to do with the concept of the light year.
Which is a measure of distance. It's how far light travels in 1 year.
Right. It's a measure of distance.
Amazing.
But because light has a strict speed limit in the universe, looking out into space is literally the only way a human being can look back in time.
It takes time for the light from those stars to cross the freezing void and actually reach your eyes.
Oh, wow. I love thinking about this.
When you step outside in India tonight and find Sirius, the light hitting your eye did not leave Sirius today. It took 8.6 years to cross the gap.
So you are seeing Sirius exactly as it looked 8.6 years ago. You are seeing it in the past.
Precisely.
So when I look at Betelgeuse or the stars in Orion,
You are seeing light that left those stars centuries ago, before the Industrial Revolution, before modern history.
that's crazy.
And when you look at that faint band of the Milky Way, the photons hitting your retina have been traveling through the dark for tens of thousands of years.
The night sky isn't a picture of the present.
No. It is a literal, visible timeline of the universe's past, with all these different eras of history arriving at your eyes at the exact same synchronized moment.
That flat, comforting, two-dimensional map we expect from our phones. It doesn't just fail to capture the three-dimensional depth of space. It completely fails
Yeah.
to capture the fourth dimension.
Absolute.
You aren't just navigating distance when you look up, you are navigating time. So tonight, grab your phone, download a stargazing app, step outside, and take a walk through time. Catch you on the next deep dive.